In this video, I want to talk about the periodic properties of elements and how that relates to where they are placed on the periodic table. Now, you already know that the periodic table is organized by increasing atomic number. So we start with one atomic number of one or one proton found in hydrogen and move across the periodic table and each row at a time, counting up to 118. You know that the groups or the columns in the periodic table are elements that share similar chemical properties. So all of our noble gases over here on the end are not very reactive, and on the other side, all of these metals are very reactive. And you know that the rows or the periods in the periodic table are connected to increasing number of energy levels, or how the electrons are arranged around the nucleus of the atom. But there are other trends or repeating patterns that were discovered among these elements that helped in the development of the periodic table and actually allowed scientists in the past to predict characteristics of elements that they hadn't discovered yet. The periodic trends that I want to talk about are ionization potential, electron affinity, electronegativity, radius of both atoms and ions, and then putting that all together, talking about the degree of metallic or non-metallic character. These repeating periodic trends are also known as periodicity, and we see them as we go across a period or down a column. Let's start with ionization energy. Ionization energy represents the amount of energy needed to remove one electron from an atom to make a positive ion or a cation. Elements that have fewer valence electrons, those are the electrons on the outermost energy level, or elements with a larger number of energy levels, so electrons are further and further away from the nucleus, have lower ionization energy. So if we look at the periodic table as a whole, we see ionization energy increasing as we move across the period from left to right, or moving up from bottom to top on any particular group. If we actually took the data of the ionization energy, we would end up with a graph that looks something like this. And notice that the high point for each, zigzag on the graph are the noble gases, except for this weirdo of mercury over here. Ionization energy is influenced by both the size of the nucleus, how many positive charged protons are hanging on to those electrons, and the distance of the electrons from the nucleus, or how far away, how long that hold has to be. So because your noble gases they're at the end of the period, so they have the largest nucleus, that is what allows them to have the highest ionization energy. A related characteristic is known as electron affinity. When you add an electron to an atom, and this is what happens to make a negative ion or an anion, it usually releases energy. So it takes energy. You have to put energy in to pull an electron away, but if you can stick an electron on, you usually get some energy back for it. And this energy change is called electron affinity. Nonmetals tend to form negative anions, and so they have higher electron affinity. In fact, fluorine is at the top here. Electron affinity is measured as energy. Energy is measured in kilojoules per mole, which is a unit that we'll be dealing with a little bit more in the second half of this course. And it is also given as a negative value, not because there's a negative it's not related to negative and positives as we usually think of it in math, but whenever energy is released, it is listed as a negative value. So nonmetals have higher electron affinity because they are able to give off more energy when they add that electron. Another characteristic, again, we're talking about electrons, is electronegativity, which is the measure of the ability of an atom to attract an electron in a covalent bond. So covalent molecules, remember, are only dealing with these nonmetals over here on the far right-hand corner. And so they are not forming ions. They are connecting together by sharing electrons. But you still see the same pattern as an ionization energy in that electronegativity increases as you move from left to right across the periodic table and from bottom to top in any particular column. Electronegativity is influenced again by the size of the nucleus compared to the number of energy levels, because a larger number of protons are going to be able to hang on to those electrons better in a covalent bond, and the smaller number of energy levels means the closer those electrons are to that nucleus. So again, more grabbing power or higher electronegativity. Atomic radius refers to how large, what is the radius of the atom, thinking of it as roughly as a sphere. And as the atomic number increases, the atomic radius actually decreases, because you have more protons in that nucleus pulling on those electrons and pulling those negative charges in, because negative and positive charges attract. So larger nuclei will pull in electrons more and have a smaller radius. Also, logically, your radius will increase as you add more energy levels. So as you go down any column into a higher period, you're going to see a larger radius. So this version of the periodic table gives you a very nice picture of what some of the differences in sizes of atomic radii. As you move from left to right across the periodic table, you can see that there's a distinct difference in how well those electrons are being pulled in by the larger nuclei. Then we have ionic radius. What do the ions look like as compared to the neutral atom? Well, positive ions have lost an electron, and so they are smaller than the neutral atom, because the remaining electrons are pulled closer to that more positive nucleus. Now it has more protons and electrons in the overall atom, and so those positive charges pull on the electrons harder. The ion also may have lost an energy level, and that you'll have a smaller electron cloud, because there is not that additional energy level, depending upon what the valence electron situation was with that ion. In opposite comparison, negative ions, where you've added an electron, are going to be larger than the neutral atom, because now you've got more electrons repelling each other, and since they are the same charge, they are not going to want to be close to each other, so that's actually going to expand the electron cloud. So this illustration has the neutral atom on the left and the ion on the right, so we can compare what happens to our positive ion as it loses an electron and becomes smaller, and our negative ion as it gains an electron and becomes larger. So all these different characteristics work together to kind of give us the perfect metal or nonmetal. Metals in general are characterized by a high reactivity, where electrons are given up to form cations or positive ions. And then nonmetals are characterized by reactivity, where the electrons are gained either to form anions or be shared between nonmetal atoms in covalent bonds. So looking at the periodic table as a whole, the degree of metallic character, or the degree of reactivity to easily give up electrons, will decrease as you move from left to right and from bottom to top, and a non-metallic character will increase in that same pattern. This leaves us with cesium down in the bottom left-hand corner as the most reactive metal. Francium is actually probably more reactive, but it decays very quickly. It's radioactive, and we just haven't studied it that much. It's just not that much around in the world. And then fluorine is the most reactive nonmetal in kind of the top right-hand corner, because the noble gases, since they're noble gases because they don't react, they don't get included in this particular discussion of metallic and nonmetallic character. So putting that all together on one chart, we can see, moving bottom to top or top to bottom or left to right, we've got ionization energy increasing as we move towards metals, from metals to nonmetals. Electron affinity, the energy that's given off as you accept an electron, also increasing together. You see also the same thing happening moving bottom to top in any particular group. And atomic radius will be decreasing as the electrons are pulled in closer to the nucleus by atoms that have more protons, giving us, cesium is down here in this corner as our most reactive metal, and as fluorine over here as our most reactive nonmetal. So in summary, the periodic trends are really a visible expression of this interaction between protons and electrons in an atom or in an ion. And these periodic trends were used in the past to predict the characteristics of unknown elements, things that had not been discovered yet, but scientists realized that something would fit right here in the periodic table. Nowadays, we still can use periodic trends to predict how new combinations of elements will react because it gives us some idea about how these elements and protons are going to behave if we create something new.